Hi, I'm Evan Sheriff, and today I'll be giving an introduction to measuring sea level and establishing datum from that. This is an interesting field that is the confluence of oceanography and geodesy. Geodesy is going to serve as one of the foundational sciences for this introduction into sea level and datums. And geodesy is the scientific discipline that's responsible for determining the Earth's geometric shape, its orientation in space, and its gravitational field. And there are a couple important misconceptions to dispel first about the Earth. First is that the Earth is not a perfect sphere. It is actually an oblate spheroid, which can be approximated with an ellipsoidal mathematical model. And this is due to the Earth's rotation and the centrifugal force, which forces it out to bulge around the center. And it's about a 1 to 300 bulge. So if we take a look at the axes, the polar axis is the minor axis, and that is shorter than the major axis, which runs along the equator. And another important thing to note is that gravitational variation across the Earth is not uniform, but it is varying at different places on the Earth's surface, and this is due to Earth's internal density variation as well as the distribution of Earth's crustal mass. And let's take a look at sea level definition. Sea level is not just sea level. There are three major types of sea level. The first one is global sea level, which is the average height of the Earth's oceans relative to the Earth's center. This is what's generally known as eustatic sea level, and anytime you hear anything referring to sea level rise or change in the world's sea level, that's generally referring to global sea level. There's also local sea level, also known as relative sea level. And this is the height of seawater that's relative to a fixed point on land that is used as a continuous reference, as well as mean sea level, which is the average height of seawater relative to a fixed datum established by a statistical average of water heights over a specific period of time. Mean sea level is the datum is the water level that's used to establish a geodetic datum. Now, exactly what is a datum? Basically, a datum is a coordinate system with an arbitrary reference surface. A datum establishes the base elevation or a base level from which different activities can occur, including mapping, data collecting, surveying, navigation, etc. Those are all foundational based upon datums. And there are two types of datums. A datum can either be a horizontal position, that is, it measures your position within space, your latitude and longitude, or it can be a vertical datum, which measures your elevation, or how far above or below you are of that reference base elevation or level. Now, there's an important distinction that we have to make here, and that'll come into play later in this presentation, and that is a geodetic vertical datum typically measures land elevation, or elevation to a fixed point on Earth or a fixed surface, whereas a water vertical datum is used for bathymetric data, and that's accounted for a little bit differently, and we'll get into that further in this presentation. Another thing that's very important and is also very interesting is that when most people think of sea level, they think of a very flat planar surface, when in fact it's not. The sea level is not level. It's a very irregular surface with a lot of lumps and bumps. And in fact, if we take away all wave factors on Earth, the range of topographic variation is anywhere between plus and minus 2 meters, so it's fairly significant. And this is due to various physical processes, including currents, various types of water temperatures, so the thermal expansion and contraction of water, the salinity differences, as well as atmospheric pressure. And the reason that these are resulting in topographic differences is basically the result of these processes being very uneven and occurring in different intensities in different places. Now, this diagram here gives you a basic overview of the different global major changes in ocean topography. So you can see there's a pretty decent range to sea level. And now this brings us to geoid. Now, the geoid is a very critical concept in geodesy, and that is Earth's ocean surface. It's an approximation of Earth's ocean surface if the only influences upon it were gravity and rotation. And in fact, the greatest influence on ocean topography is gravity. Gravity variances tend to pull water, and that's both real influence, so in the world as we see it now, and that geoid approximation of Earth's sea level if it was to cover the entire world. So geoid is an approximate mean sea level, and it's used to establish geodetic datum, and the geoid can actually vary up to 100 meters globally. So if we take a look at this diagram on the right-hand side, we can see this is really what the Earth looks like. It's not a perfect sphere, it's not a perfect ellipsoid, it's lumpy, and it's varying quite a bit. Now this picture is exaggerated 1,000 times, but it gives you an idea of really how important gravity is in shaping the Earth that we have. And this is just a diagram basically of how this can possibly work. Here we see a seamount, so we're going to have more crustal massing there, and that'll create more gravitational force. And you can see that as opposed to the flat ocean floor, that seamount will deflect those gravity vectors, and those deflected gravity vectors will pull that surface water towards it, that ocean water towards it, creating that bulge, as well as that being part of what creates ocean topography. And now this is a very intuitive diagram that can help illustrate the differences between the actual surface of the Earth, so we can see that brown area, which is the actual varying surface of the Earth. Then we have that ellipsoid below it, and that green dashed line. So that's that ellipsoid, that is that mathematical approximation of that flattened sphere that Earth really is. And then finally we have that geoid, which is that blue dotted line. And that is that geoid model that approximates the mean sea level if it was affected only by Earth's rotation and gravitational pull. And so that's that mean sea level distributed throughout the world. And we can see that it is indeed varying. It's not perfect, it's not clean, it's a very dynamic process. And now bringing us to local sea level, and as we mentioned earlier, local sea level is that level of the water which is referenced to a fixed point on land. And again, the natural processes previously related do affect it here, but one important difference is that tides play a very major level in both affecting the sea level as well as measuring the sea level. But another important thing to take into account here is the vertical land motion, because with local sea level, we're referencing that level of the sea to a fixed point continuously on land. And of course, land itself is not stable. You have, of course, continental drift and other tectonic and geologic forces acting on it. And what's very important here is the vertical motion. Now, obviously, during the last ice age, much of North America was covered with glaciers, and this has caused isostatic rebound to come into play here, because we have a lot of northern areas that are actually moving up and rebounding, whereas we have other areas which are subsiding, such as places including New York and much of Louisiana. So that is going to affect local sea level. And the local sea level is based off of a tidal datum. So you're measuring these different tides, and we can see in the diagram here different aspects of the tides that are measured. So different areas of the tide. And what most people are familiar with and what we dealt with in the course was mean lower water. And this is accomplished through using tide gauges, but one important thing to note here is that there has to be a national tidal datum epoch, which is a 19-year period of continuous tidal observation averaging. So the NTDD is updated every 20 years, and the current one is a little bit older, but we'll be coming into the next one shortly once that data from 2002 to 2020 is processed. Now the NTDE accounts for an 18.6-year lunar node cycle, as well as each year there is an annual solar declination cycle that also needs to be accounted for. So that's rounded out to 19 years of tidal observations that are then accounted for. So from that data, you can then derive all of these different points: highest observed, mean higher high water, mean lower low water, etc. Now looking at a tide gauge, traditionally these were mechanical floats which would sit in a stilling well to calm the water, and they recorded on a running pen ink strip chart. Now that was a mechanical process, often faulted, but now in the modern era we are using acoustic signals which are sent down an internal sounding tube, as we can see in this diagram over here on the right. So that tube itself is in a stilling well to ensure that it stays as isolated from other dynamic forces as possible. And what this does is that acoustic signal is sent from the receiver on top. It hits the water in that sounding tube and will come back and bounce back to the receiver, and the receiver will measure the time that it takes that signal to return and will then compute the water. And the real advantage here is you've got computerized data logging, so it's more accurate, and it's also much more on point as far as the timing is concerned. And these tide gauges are usually measured at 6-minute intervals, and those are controlled by satellites, so they are very accurate. Now, these tide gauges are used to establish those local sea level datums, which we discussed earlier. So they'll measure continually for 19 years, and you'll take that 19-year chunk and establish those datums. Now, each of these tide gauges is part of the National Water Level Observation Network, which is operated by NOAA, and it accounts for 210 observation stations across the United States. And now these water level datums, these local water level datums, are used for nautical charts, where you're presenting that bathymetric data, where you have to have a datum that is accounting for the actual surface of the water, not an approximated or calculated mean sea level. Additionally, tide tables and predictions are based off of this. Water level predictions are also based off of this. And these also come into very key plays during emergency and storm response. And here we can see a map of the 210 tidal stations across the United States, as well as on the left a reinforced tide gauge, which is designed to withstand storms and can continue processing and logging data even during extreme conditions, providing for that continual operability. Now, of course, as we mentioned earlier, vertical land movement is very important in considering local tidal datums, relative tidal datums, and to determine the land movement, that's geodetic surveying, very accurate geodetic surveying techniques are used, and that can also link land coordinate systems to these tidal datums and water datums. Now, how do we measure, as we mentioned earlier, that larger sea level topography? That is generally done from satellites, because that can't easily be done from the ocean surface, and in fact, it's really impossible for many people to even detect topographic variations on the sea surface. So there are several satellites, many are operated by NASA, that use a satellite altimeter. So what that does is it sends out microwaves, in this case, in many cases, 1,700 microwaves per second, and it will beam that down to the ocean surface, then it'll bounce back, and the altimeter will calculate how long it took that signal to return and get a distance off of that. Now, additionally, these are equipped with radiometers, which will monitor atmospheric conditions and water vapor contents, and will then apply a correction to ensure the most accurate data possible. Another aspect is precision GPS positioning. These satellites are able to be positioned very accurately in space, and they're actually referenced to the ellipsoid. So what will happen is they measure to the top of the sea surface, and then taking that distance and the distance to the ellipsoid, they'll subtract that and create a mathematical correction so that the actual topo position is calculated. Now, the accuracy from a single measurement is plus or 2 minus centimeters, which is pretty incredible all the way from space. But if they actually average 10 days of data, they can get to plus or minus several millimeters, which is an incredible accuracy. And here we can see another diagram which highlights the functionality of this a little bit better. And this brings us to the geoid. And as we previously mentioned, and I'm going to reiterate that here, is the geoid is the mean sea level of Earth. It was influenced only by gravity and Earth's rotation. Now, this is what serves as the geodetic vertical datum, which is essentially the approximation for all types of different activities from aviation, navigation, mapping, surveying, and it determines most elevations that are used across the world outside of those for bathymetric or hydrographic data. And these are developed with gravity surveys and gravimetric data because, again, the main differentiating factor that occurs here is the gravity variations that occur across Earth. And in 2022, NOAA is going to be coming out with a new geoid which has plus or minus 2 centimeter national vertical average anywhere in the United States. And here we can see how NOAA conducts most of their gravity surveys, and they do it via aerial aircraft platforms to cover the massive areas that they need to. And finally, just going to leave off with a couple of institutions here. NOAA Tides and Currents is a great resource if you want to get tidal data, especially for navigation or those tidal cycles. For geodesy and those geoid predictions, the National Geodetic Survey is your place to go, and then NASA has a lot of that sea level change and studies in great detail the topography from space.